Hi, and welcome to this video where I'm going to demonstrate how to query the Nomad archive from the Nomad Artificial Intelligence Toolkit. As you might already know, one specific feature of the Nomad AI Toolkit is that it allows to query the Nomad archive. And in this video, I will demonstrate how to do this in practice and will show you an example of machine learning analysis on data just retrieved from the Nomad archive. Starting from the main page of the Nomad AI Toolkit that you can see now on the screen, you can click on the Query the Archive button, and this will readdress to a Jupyter notebook that will demonstrate how to query the archive, and we'll also see an example of machine learning analysis. The first step is to import all the packages that are going to be used in this notebook. So we can see here things as pandas, it is the most common data science Python library, and also sklearn that contains most of the most popular machine learning methodologies. Here we import all the Python packages that are allows to query, to interact with the Nomad API. And all these packages are all already available and installed in the Nomad AI Toolkit. Here we also import the atomic features package. This will give you all the atomic properties that we will use in our machine learning analysis. And the reason is that one of the main goals of performing machine learning analysis on material science is that we would like to predict materials property given the atomic composition and atomic features of the material. And here we're gonna take all the atomic features that will be used in our analysis. So in this heat map, we can see the values of here the feature we are analyzing is the atomic number, that is the most trivial, and you can see how it changes color in the with the periodic table. But then we can also take other properties, as for example the ionic potential, and then if we hover over the elements, we can see the value of the ionic potential. If you are more curious to know how these data are obtained and all the functionalities that are included in the atomic features package, I will recommend you to visit the AI Toolkit and go through a tutorial that explains how this package is structured. Okay, so now let's go back to our query. In this cell, we define all the query parameters of our query. And we can see that we are asking that all simulations, all the materials that we are going to retrieve were obtained using the VASP code. We also asked all materials contain oxygen, that the crystal system is cubic, that materials are ternary, so contains only 3 different elements, that the XC functional is the GGA, and then this is also very important. We are ensuring that simulations have converged. So we have this geometry optimization. We are essentially asking that all simulations retrieved have converged within this value of to the 10 minus 22 in joule. But so now you might demand how to obtain this script here. Well, this is something that you can get from using a GUI that is accessible from the nomadlab.eu website. As you are currently using the version 1 of the Nomad API, you firstly should go here and access the newer API version. And from here, you can make your querying using GUI that is accessible from Explorer entries. So here we define our query essentially. As a first thing, you can see that we have initially all materials that are over 12 millions, that are all the entries in our Nomad archive. And then here we start making selections. So we see that oxygen, we ask that there is oxygen in our query. So each material should contain oxygen. And then we also demand that materials are ternary, so at most 3 elements and at minimum also 3 elements. And now we already see that we have less than 1 million different results. Then we keep with our query, so we say here that the system is cubic. code uses wasp, and the GGA functional. And then we also demand that simulations have converged. Here we have electron volts, but we're working with Joule, so we change the units. And we simply put here 2 minus 22, and that's our query. You see that now we have almost 9,000 results. What is really interesting about this is that we can also check the author and the origin. And we can see that this came from 3 different databases, the Materials Project, AFlow, and OQMD. And this is something that is very specific of the GNOME AI-toolkit, that is the largest material science database, and it has very heterogeneous sources of code, of uploaders. From here, we can access the snippet code that we use. So clicking on that button, we have this code, and this is essentially what was defined in our query. So you simply then have to copy paste this and putting it here. And that's how we define this query variable. Then here below we have some required field. Required essentially says what is going to be retrieved from the query. So we see that we have things as the space group number and the final energy difference of the geometry optimization, chemical composition, and the position of the atoms. This is part of this workflow section. So it means that these positions of the atoms are the position of the atoms and the simulations that has finally converged. So now how we can identify what kind of entries to retrieve. Again, coming back from the GNOME Lab webpage, again in our API 1, we can have here the access the GNOME meta info, and here we have the schema that is used to store all values. So results give so from entry, so each entry is the basis, and then we have things as results that gives an overview of all the results, and then we said that we were looking for the space group number, which is this one here. Then again, we can also access the workflow, which is then pointing to, if we take calculation results and reference section, and then we go to the base calculation, it is pointing to the calculation, this base calculation, that has converged in our simulation. And from here, then we can access all the values as that we retrieved from system ref are about the system. So here the atom's position and the chemical composition. But then you can also find here things as the energy, forces, stress, and all possible entries and values that can be computing with a DFT simulations. So here we decide what kind of entries to retrieve. So I would like to mention we chose the space group number. This is always an interesting quantity to study for materials. And then the atoms positions and lattice vectors, which will allow us to compute the atomic density of the material. So the atomic density will be the target property, a material's property we will study as a function of the atomistic composition, because the atomic concentration is something that depends on the interatomic interactions of the material. And this is something that is not trivial to compute, given solely the atomistic composition. And we would like to create a machine learning model that is capable of doing this. Then we set here the max entries, that is 9,000, a bit more than what we've seen before. This is just a limit that is used for security reasons. And then page size that essentially says how many entries are retrieved at each API call. And then we fetch our query. We define some scale factor that is used for numerical stability as we change our values in our reference system, because you want to work on machine learning with values that are too small for convergence. And here, in this cell here, we construct the pandas data frame that will be the basis of the analysis. So we download the query, and then we here we perform a lazy query. So step after step, with this entry is retrieving data from results that is here. So then here we essentially creating this variable that contains all the values defined in the required field. And then this, for example, will allow us to compute the atomic density. In this script here, we create a file that stores the atomic position of the simulation test converged. And this is something will be used by the visualizer to make a visual inspection of the material that is studied. Then we label the elements in our material. As we said, we have three different elements. We have oxygen and two more, which are the label A and B. This one then will be used by the atomic features library for retrieving the element-specific the atomic properties that will be used for during the machine learning analysis. Then here we have the stoichiometric ratio of the material. And then we take all these elements and values that we computed and retrieved to fill an entry of the pandas data frame, step after step in this for loop. So we have things that are taken from the atomic features package as the ionic energy of the element A and B, and then things that we also just retrieved from the Nomad archive as for example, the space group number or the atomic density that we also computed from the lattice vectors. So as this query can take some minutes, we skip over it and we just use some cached data that are saved in the AI-toolkit. So this pandas data frame, the result of this query, is already cached. We give a brief, we take a look at this, how it is structured, this pandas data frame, using the describe function. And then we start analyzing the values that are more interesting for us. That is the space group number, so in this histogram. And we see that, in fact, we only have mainly two different space group numbers, 221 and 227, and many others that are almost irrelevant. This is something interesting. We would like to understand better about this composition. And then we also analyze the atomic density. And you can see that we have quite some spread values, almost like a Gaussian, you might see, which is also involves, as the values are not too peak around the value, that probably this machine learning analysis is not too trivial. As all these values were uploaded by many different people and they were all using different parameters for the queries, we might have the same material that has been simulated by different person, different settings of the computational simulation. But still, we would like to have one entry for each material. So what we do, we average for all these materials that have the same chemical composition, we average our target properties, that is the atomic density. And then to get like a reduced pandas data frame that is the F group here. So now we can we can finally make our clustering analysis. In this case, we are using the HDB scan clustering algorithm, and which finds here two clusters. And then we reduce our and here we reduce, we use also some dimensional reduction algorithm, UMAP, to reduce the space onto a two-dimensional space. So here we see that we've taken 7 features, so we are in a 7-dimensional space, and this is something we cannot visualize. We cannot make a visual inspection of such a space, and this is something we might want to have. This is something that can help us. So here we are using HDB scan for clustering, and if you're curious more about clustering, I really recommend to go through our introduction to clustering notebook in the AI toolkit. And this HDB scan, which is also explained in this notebook, it is a clustering algorithm that is able to identify outliers, and removing these outliers is able to create some classes that are more distinct. So cluster analysis, what it's doing is finding some groups of elements, of materials, that in our 7-dimensional feature space are so much close to each other. So we would like to have to see some materials where all of them are similar to each other that are different to other groups of materials. And this HDB scan is capable of finding these clusters. But then we also would like not only to know, here we see that we have two clusters, we would like not only to see how many clusters and then making some quantitative analysis on it. We also would like to visualize it on a two-dimensional map because this is something very useful. We will see why now. And we use UMAP, which is a recent algorithm that allows to project this larger space, a dimensional space, on a two-dimensional embedding, trying to preserve the relative distance. And now we can visualize our data using our visualizer. So here we have some color features that we will see what will be about soon with atomic density and space group number, and then hover features where we have things as the atomic number and space group number. It is something that you can also change. So here, this is the results. So we can see that in fact we have two groups of materials. So here the colors are the different classes, and we see that in fact the clusters that were identified by HDB scan are so most distinct also by UMAP. And those are two different techniques that found this. So, and this is interesting because it is gives more strength to this identification. If you look at outliers, then we see that in fact there is another cluster of elements here that are not identified as a cluster but just as outliers. And this is also the difference of just like looking at the map and making clustering on a 7-dimensional space and then projecting. So you see that making the clustering in the 7-dimensional space, it allows to find the cluster, and then we can visualize on a 2-dimensional map that can give misleading results. So we might think that this is some elements that have some similarities in a high-dimensional space, but maybe they're not. They're just an artifact of the two-dimensional projection. But so now we would like also to see how what are these clusters about. And then if we look at the space group number, it is interesting to see that the two clusters have essentially different values. So here we hover over the dataset and we see that the space group number 227, and this is for pretty much all these points, the yellow color, while the green color here has space group number 221. This is something that we will see more depth later. Another feature of this visualize is that also we can decide the fraction of elements that are visualized. This is because we don't want to visualize too many points which are heavy to load. Then if we click on a point, we can make a visual inspection of the material, as you can see here. And also the other way around, so you can also select a material here. For example, you might want to have something, you can, and then you can display it, and then you find it here. So this cross is this one here. It appears also on the map. So, and then you can also, if you click here and click on this other, you can see another this structure. And this allows to inspect one after the other all the materials. Then if you click on this button here, we have a number of tools for creating high quality plots, and we'll invite you to explore all this functionality. And then you can print it with also scale that it identifies the resolution of your plot. And this will then allow you to download in the format that you desire your dataset, and that you can see it here now. Now let's come back to our analysis. And now we would like to see how the clusters are composed. We can see that most of the clusters here have in fact two different values, 221 and 227. And if we look in more depth, we can see that with this pie chart that in fact are almost all composed, like one cluster by space group 227 and the other 221. If we make the same analysis on the outliers, we will see that not only there are both none of them is real in majority respect to the other, but there are many, many more of all the others. So it's able to take all these values out, the clustering algorithm. This is interesting because it shows that the space group number is somehow also a result of the chemical composition of the material. Because when we are done this analysis, this exploratory analysis, we didn't put the information, the space group number, as the input of the machine learning model. And so this involves, it must be some correlation between the chemical composition and the space group number. That is a material property. So now we are finally making our machine learning analysis, and here are the features that are selected for, this is the atomic features that you can see are only atomic features, and this will be used to compute the atomic density. This is a material property. This is the target feature. And we divide the test set and train set with a difference of 0.2. And finally, we can use random forest. And if you're curious about random forest, we also have a dedicated notebook that explains in detail how random forest works. And we can see this is the accuracy we have in the test set and train set, which is quite a good accuracy. So I would like to mention that on test set, it means that the machine learning model was not trained on that test set, and then we make prediction on data that is unknown to the model, but we already know the results of the density of the material. And then finally, we would like also to have a final representation, and in this graph, we can see that we have some AI prediction reference values. So now I will explain you what this means. We know that we have three different elements. We have oxygen and two more. So what we have on the x-axis is the one element, and then we take the average over all the other values. So we have A, that is, for example, atomic number 3, and then we make the average over all the other second element B in our ternary material. Then we have a mean, and then some variance, of course, of the atomic density. The same was done with reference values, so the values that were were used for training the model, and then also on the AI prediction, that is just the prediction of our model on the test set. And we can see not only that we have quite some good agreement in the mean and the variance, but also something interesting that we see is that we have some trends that follows the periodic table. So this again, it means that this atomic density can be correlated to some chemical properties of the other material that are uh, um, in the material with the oxygen. So now this was all. I really hope that you learn how to perform machine learning analysis on data that were queried from the Nomad archive, and this will inspire you for next applications of the AI toolkit for your own project. And this was all. Thank you for the attention. Hi, welcome to this video where I'm going to demonstrate how to use the Nomad AI Toolkit app. As you might already know, the Nomad AI Toolkit is a web-based infrastructure that allows to deploy machine learning methodologies on material science data. When you're accessing the Nomad AI Toolkit from a browser, all the calculations that are performed with the AI Toolkit are then in practice carried out on a cluster that is located in Garching at a Max Planck Institute. However, in certain case, you might desire that to use the Nomad AI Toolkit on your local machine. This could be the case where you don't want your data to access the internet. Or, for example, you might just desire to use all the computational power of your local machine. In all of these cases and many others, you might want to use a local installation of the Nomad AI Toolkit. And this is possible, and we're going to see how this can be done with very simple steps. The starting point is this web page. It is the Nomad GitLab repository. And you can access it from the address that you can see now in red on the screen, that is gitlab.mpcdf.mpg.day/nomadlab/AI-toolkit-app. From here, you can find this is a GitLab repository, and you can find a README file that is the basis that explains how to use it. And I really recommend that you read this first. But now we're also going to see in practice how this can be done. You should first clone this repository, and this is a public repository, so everyone is allowed to access it and clone it. So now you can see on the terminal that I'm cloning it. Then you move into this directory. What you have to do, it's very simple. You just have to launch this Docker Compose app. So a necessary requirement to use the app is to have in your machine installed Docker. And in this case, you see that the images that are used by the app have been immediately downloaded in my case. However, the first time that you will do it, you might have to wait some minutes, 10, 15 minutes, because the images are over 10 gigabyte space. So it needs some time to be downloaded from the internet. So far we have accessed the internet, and but from now on, when we downloaded the images and this clone this GitLab repository, we can start working on our local machine. And to access after opening it, this Docker Compose, these Docker containers, after creating it, you can access the app from a local port from this address, this local host that you find it on the web page. And then you access the Nomad AI Toolkit app that is on your local machine. Now we are not anymore connected to the internet. You can see that the GUI is the same as the web-based version. So you can browse over all the different tutorials, and all the tutorials have the same installation, the same packages, and you can exploring and learning the basis and the most advanced applications of machine learning to material science on your local machine. You can also modify this tutorial as you wish, and then trying the same methodologies on different applications. However, as also for the Nomad AI Toolkit app, you web-based version, when you restart the image, then you will find all the tutorial in the original version. It is good because then you have again the working versions of our machine learning demonstrations. But then you might also want to have a way to connect with your computer, with your machine, to import your data and save your progress. And for doing so, we have this get to work directory that you can access clicking this button here to the right. And this is a connection from the AI Toolkit app and your local machine. So now let's see in practice what I mean. Still from the terminal, we open a new window, and we see this, that we are located in the directory we downloaded it, and then we can find all the different files and directory, and then we move in the work directory where we are now with the browser. And now here we find exactly the same file. You can see this assets directory in a welcome notebook. But then you might create a new file. And then this is something that you also can find here on the directory. This is what we just created. And this allows to, for example, you can bring your data in the work directory and then access the directory from the AI Toolkit app. So now we can see this welcome notebook that gives a demonstration of this. So here we are simply replicating some of the steps that are copy-pasted from the compress sensing tutorial, which is just applying SISO. SISO, that is a recent machine learning methodologies that is also demonstrated, that has been developed in the Nomad laboratory. And this is an example of the applications of SISO to small dataset of material science and some octet binaries, as in the compressed sensing tutorial. And you can see that has just created a number of directories that contains the feature space and some models as the results of these calculations. And all of this, you can find it now on your work directory again. So now you might want to create a notebook, and this is something that you can find from new Python. And in this notebook, you have available all packages that are installed in the AI toolkit. So you might want to import also CISO there. And then you can perform your machine learning analysis on your own dataset. Or if you don't want to use CISO, you can also, I don't know, you can take, for example, some of the example of random forest. And again, this is something that you can copy paste all the cells that you can find in our notebooks and just deploy them in this new tutorial, this new notebook, giving any possible combination of all the methodologies that you can find here. So now we can close our container and once we close this, where we just use Control C, we can see that we don't have any more access to all of this now. Our app is not connected anymore. However, once we're here and we go to the work directory, we still find all material that we just created, and we can reaccess it again with the AI-toolkit app. With this was all. I really hope that you learned that you enjoyed the video and learned how to use the AI-toolkit app, and that this technology will really help you to progress with your projects. Thank you for the attention.